Nachitor from TriMech Solutions. Welcome to the webinar on what's new in Simulation 2016 for SolidWorks. I hope you all had a preview or first look at some of the capabilities associated with the 2016 version of SolidWorks. Today, we're going to go through and review some of the key enhancements in all the simulation products offered by SolidWorks for the year 2016. The theme for the year 2016 has been to make great design happen in terms of design, validation, communication, or collaboration of information and building the same data. And today, as I mentioned earlier, we're going to focus on the validation aspect of 2016 SolidWorks simulation. First, we're going to start with structural simulation and go through the enhancements, and then I would jump to plastics tool, and eventually we'll finish with the enhancements for flow simulation. SolidWorks structural simulation has been quite successful in terms of its capabilities, in terms of its ease of use for the users over so many years. In 2016, there has been some really slick enhancements to improve or to enhance the power of the tool. The first one, which in my opinion is probably one of the best enhancements for 2016, is the ability to activate as well as deactivate reference geometry fixtures in the nonlinear tool in SolidWorks simulation. What this means is the user can now turn on or turn off certain fixtures in between different time steps in a nonlinear study. To see how this functions, let's go ahead and take a look at the nonlinear tool in 2016. All right, as you look at the interface, it looks very similar to what we've been used to, a little bit more gray and polished in terms of the design, but as far as the placement of the icons or interface-based items goes, it's been pretty much the same as far as simulation is concerned. Now, for this particular example, wherein I have a clip getting locked into this pin located in this location, I've basically set up two different reference geometries, one for the clip, as you can see, being applied on the edge of this 2D simulation. And in the past, we've been able to control the reference fixtures in terms of time. But now in 2016, what we can do is, if you look at the reference fixture for the second item right here, the user has the ability to turn off or turn on the movements or the fixtures or the restraints of a particular simulation during a specified time frame in a nonlinear step or a nonlinear analysis, which means when I take a look at the results, I can basically animate or simulate the motion of one component over the other, and also turn off a particular fixture in order to kind of lock down a particular process for a few seconds. As you can see right here, the fixture was locked down and now it's back in space. All right. This lockdown capability, where the user can turn on or turn off various reference fixtures, increases the capability of the nonlinear tool. Not only that, it also improves the overall accuracy of such simulations and also provides the most accurate load transfer between multiple components wherever this particular feature is being used in a nonlinear analysis. Our next enhancement for the structural simulation tool is the introduction of blended curvature-based mesher. What this means is, in the past, we've had two types of meshing algorithms, which are standard and curvature-based mesh. The blended curvature-based mesh essentially identifies the areas of high geometric gradients and refines those particular regions while keeping all the other areas fairly either at a default or a coarse mesh configuration, which not only saves time during the solving phase, but also reduces the number of elements in the mesh. Let's go ahead and take a look at this real quick. So in here, I have a arm that's used to transfer the bending loads in a torque-based application. And if I look at my meshing option or my meshing tool, when I go to create mesh, now in 2016, it's going to give me an additional option under meshing parameters, which will allow the user to select the blended curvature-based mesh. All right, let's try this real quick. Right here, under mesh parameters, as you can see, you now have option for a blended curvature-based mesh. As mentioned earlier, this algorithm not only reduces the number of elements, but also saves a lot of time when you're actually solving the problem. So that's how one can access blended curvature-based mesh in 2016. Next up is probably one of the most popular enhancement requests, which was to introduce the ability to view the mesh configuration through the thickness of the model. I believe this has been a really popular enhancement request from the last couple of years, and SolidWorks took this suggestion from the users and converted this into an actual enhancement in 2016. What this means is, in the past, we were able to view or superimpose the mesh on top of the results, and that was it. When we created a section of our results, we were not able to see the actual mesh configuration on that section. Also, when we were just trying to view the mesh, we couldn't see the mesh elements through the thickness or across the thickness of different components. But in 2016, as you're going to see, you can actually visualize the mesh through the section. You can access this feature in multiple different ways. The first method is if you right-click your mesh feature in your simulation feature tree, and then select mesh plots. That will basically create a regular mesh plot, or when you hit show mesh, that would work too. And then when you right click the mesh plot and activate it, you would get an option to actually see the section view of this mesh. All right, and I had basically turned on by right click this guy and selecting mesh sectioning option. This basically allows user to select different planes through which they can create sectional plot across the thickness of the mesh. You can use either this arrow mark to drag and drop or offset the plane where you actually want to see the mesh elements through the thickness, or you can switch the planes and change the dimensions of the section using these parameters right here. Now the cool part about this is when you zoom in, you're actually able to see the fineness or the coarseness of the mesh along different sections. All right, so that's the first method. Method number two is, this method is not just limited to viewing mesh when the results are not loaded. You can also do the other way around, wherein, let's say you open up your stress plot or displacement plot, and then in the past we were able to just superimpose the mesh on top of the existing result, which would be something like this. So if you right click the region and hit show mesh, you could basically see the mesh elements on the surface. Now in 2016, you can right click this guy and hit mesh sectioning, which will not only show the mesh elements across the thickness, but also superimpose the results at those locations. All right. So if I save this view and zoom in, so now I'm able to analyze and make sure that I have sufficient number of elements in this high stress concentration area for me to actually get accurate information, accurate performance out of this model. That's the method number 2, wherein you can go to your section clipping plot and turn on mesh sectioning. The third method is when you go to your section clipping, there's this checkbox that says show mesh on section plane. And what it does is, instead of showing the actual configuration, it's going to show like a surface configuration of the mesh cut right across that plane. So these are 3 different tools available to visualize the mesh quality across the thickness of the geometric parts in your simulation model. Next up is the capability of the software to automatically bond the shell edges which have predefined gaps in them. The best examples that I can think of is when you have structural elements or weldments or sheet metal components in a particular assembly. In the past, we were able to define a global contact between these components, but the problem was we had to manually do it. In 2016, you can automate this process by going to your global bonded contact settings and checking a new box that allows the user to specify non-touching faces. So let's go ahead and take a look at this guy real quick. When you go to your global contact and hit edit definition, there's a new checkbox at the bottom that says non-touching faces. This allows the user to specify a clearance between all the components right here. As you can see, there's a small gap between all these components. You can specify the minimum clearance, and if you check this box, it's going to include the contacts between all the shell edges and shell face pairs in a shell model in SolidWorks simulation. Now, the advantage is you don't have to manually define these local bonds, because the global bond itself is going to identify those edges and bond them together as long as they fall within the minimum clearance specified by the user. So that's one of the pretty cool enhancements in 2016 as far as shells are concerned. The next one is probably the best, or the rockstar enhancement for structural simulation tool in 2016. I'm sure most of you have experienced or seen the error message while running the structural simulation, which says model is unstable or unconstrained bodies and stuff like that. And what that means is essentially the number of fixtures or the contact definitions defined in the model are not sufficient. So in 2016, SolidWorks took a really nice, really slick approach to solving this problem. Basically, the user can now identify the bodies which are unconstrained and then either apply fixtures or contacts to reduce or negate the effects of free body motion of these individual components. For example, I have not created any bonding between all these elements or all these components. And what that means is when I right-click connections, there's a new option called Find Under Constrained Bodies. All right. And that's going to lead me to an interface wherein if I hit calculate, the problem or the solver actually runs through the entire model and looks for all those components which are free to move either in terms of translations in X, Y, and Z, or in terms of rotations about X, Y, and Z. So as you can see, I've got a bunch of components here which have unconstrained motion. For example, let me pick up body 1, which is this element right here, and I have 6 unconstrained or under-constrained degrees of freedom. So if I click on one of these, let's say translation 1, let's see what happens. It actually shows a really cool animation indicating the direction in which the body hasn't been constrained. And it's not just limited to translation, you can also look up rotation. It clearly shows that the body is unconstrained in terms of rotation about the y-axis. So this is a pretty impressive tool because it helps the user to identify the components that are not well restrained and fix them either using fixtures or contacts. So those were the enhancements for the structural simulation tool in 2016. Now, taking the next step, we are going to talk about the new features introduced in the injection molding or plastic simulation tool in 2016. The first enhancement is the ability for a user to define a solid geometry as a runner domain in plastic simulation. What this means is, in the past, the user had the ability to bring in a solid geometry and mention whether if it was a cavity or if it was a cooling channel or if it was an insert or mold. It's nice that in 2016 now you can define a solid geometry as a runner, which will make sure that the solver on the back end knows which is the actual injection cavity in the model. All right, let's go ahead and take a look at the setup real quick. Defining this runner functionality or runner domain is pretty simple and straightforward. When you're creating your solid mesh, all you need to do is make sure you check this box that says runner and advanced cooling system, and then you define the type of runner. And as you march ahead, under domain type, you would select all those entities which are associated with the runner and specify the domain type to be runner and hit apply. So in terms of the interface, it's very similar. You just have this added option under the list of domains shown in the model. The next neat enhancement in plastics is the improved interface overall, especially if you look at the command manager, you would notice that it's a lot cleaner. It's got more number of features associated with the actual setup of the problem. So in the past, you would just see the options starting from video recording all the way down to settings and help. Now you've got all these added options which are more frequently used by the users, which means you can set up your plastic simulation either using this simulation tree at the left or using the options under Command Manager. The next enhancement within the plastics tool is probably one of my favorite. It's basically an improved or enhanced reporting tool. In the past, we were able to right-click this report option and generate either a Microsoft Word or PowerPoint document from it. Now they've added the nice HTML file which basically pulls up the same report, but the cool part is you've got all these hyperlinks which take you to those specific paths immediately. So you can actually share these HTML files which are more organized, more professional looking, and jumping between one particular feature to another is pretty cool. So as you can see, I'm jumping from material parameters to process conditions to the flow results. to different animations that are already saved in this HTML file. Right. So those were two neat enhancements with the user interface and the reporting tool. Last but not the least is the addition of a new and improved solver to the plastics tool. Before I describe the advantages of this solver, let me go ahead and show you guys where you can actually access these different solvers in the plastics tool. So traditionally, you right-click Fill Settings, hit Open Settings, and select Solver Settings and Options to actually access all the solver-related settings. Most of the default settings work absolutely great for most of the applications that our customers deal with. But in some cases where you may have to tweak some of these parameters, you can come in under Fill Settings and select Solver Settings to tweak these options. Now, if you look at volume of fluid algorithm, this is basically the solver or the backend program that solves all or performs all the computations on the backend associated with injection simulation. If you select this drop-down menu, this is where you could access the different solvers, which were indirect and direct in the past. The new 6M solver not only improves the accuracy of the overall solution, it's also known for its improved performance, which means in your calculation time, you're going to save a significant amount of time while the problem is running, since it's faster and more accurate compared to the previous solvers. And the good news is SolidWorks has set this new solver as the default settings for all the plastics problems. That brings us to the end of the enhancements as far as plastics tool is concerned. And now we're going to jump into the last portion of this webinar, which is the enhancements in the flow simulation tool. SolidWorks Flow Simulation is a full-fledged computational fluid dynamics tool used for various applications such as aerodynamics, heat transfer modeling, thermal simulations, and air circulations or HVAC simulations. And in 2015, starting with the simplest, I would choose the mirror results enhancement. Basically, you can run a half symmetry or a quarter symmetry problem and then display the results for the full geometry. This feature has been there in the structural tool for a real long time, but from 2016 onwards, it's going to be available in the flow simulation tool as well. All right, let me go ahead and pull out this valve model, which basically shows airflow from one end to the other end of this valve. And what essentially you're going to do is you would load up your results, and for example, if you create a cut plot in your model across a particular section, like this guy, and just for your reference, I'm using a half symmetry for your problem in my computational domain. The dotted or dashed lines indicate one half has been treated as symmetry and the other half is actually being solved for. So if I open up one of my cut plots, which is created for the original model, as you can see, it shows the velocity across one half of the section. Now, if I right-click this guy and hit Edit Definition in 2016, you would see a new checkbox that says Mirror Results, which, when turned on, is going to show the results for the full geometry or the full model. It's not just limited to a static image. You can also animate the full result shown in your model. So that's one of the really neat display capabilities or display enhancements introduced in 2016. Next up is the improvement in the options provided for the transient solver. A transient solver usually makes use of different time steps to solve a large problem involving physical time as one of its calculation parameters. In the past, the users had limited control over the number of iterations that the solver takes in between every single time step in a large transient analysis, and that would increase the calculation time significantly. Now in 2016, we've got this enhancement called nested iterations, which basically allows the user to select or limit or restrict the number of iterations that the solver can perform in between individual time steps. And to access this feature, you would basically right-click Input Data, go to Calculation Control Options, select Solving, and you would see that for every time step, you can choose a nested iterations and limit the number of iterations between these time steps. And this can significantly reduce the calculation time in transient problems. So as you can see, I'm showing a comparison between 2015 and 2016 for a transient problem using this particular method. The total solver time was reduced from 36 minutes to 2 minutes for this particular problem. Next up is the ability to import sunlight properties. For those dealing with solar radiation projects, you can now kind of link the solar radiation properties into the flow simulation and perform thermal analysis. Last but not the least, one of the rockstar enhancements for flow simulation in 2016 is the ability to model equidistant mesh at a local level. What this means is, in the past, when somebody's dealing with a boundary layer problem or really high pressure gradients near the boundary of a particular geometry, if you're dealing with aerodynamic or high-end thermodynamic problems, the users had a little bit difficulty in modeling the really fine mesh around the surfaces or volumes of the geometry. We typically had to create a dummy geometry and then introduce fine refinements around this area. In 2016, you can certainly use the dummy geometry. You can also specify what we call as shell offsets and cell layers. What this means is user can specify up to 3 virtual layers, 3 virtual shells of mesh or 3 virtual envelopes of mesh, and then the user can specify the degree of mesh refinement within these shells, which means the user can specify a shell offset from the surface or the volume of the geometry, and the user can specify the number of refined cells or the refinement level within these shell layers. Let's go ahead and take a look at the setup real quick. So as you're going to see, I'll make use of the same problem that was shown in the slide, and you can notice that the interface has changed a little bit for the global mesh. It's now being shown under the regular mesh option. As far as the local mesh goes, this is where you can actually define these equidistant refinements. As I mentioned earlier, you can define up to 3 shells which will be offset from this geometry, and then you can define the number of refinement cell layers within these shells, which means you're not only specifying the offsets, but you're also specifying the degree of refinement in the mesh elements between these offsets. To give you a better understanding, let's go ahead and take a look at this slide real quick. So I've used the same model, and I started with a 1 equidistant shell right around the geometry with 1 refinement layer. Now with the same shell, when I introduce two refinement layers, you can see that a large cell here is broken twice. Every refinement means a cell is going to be broken into 4 different shells. So you can see 2 levels of refinement around this shell. And when you look at 3, you would notice that the finer elements are packed closer to the geometry. And these colors are indicating different refinement layers. And 4 refinement layers, as you can see, the number of cells have increased significantly, which means I would now be able to capture the boundary layers, the pressure differences, the recirculation zones in the most accurate way or the most efficient manner. The same problem with 3 offsets or 3 shells instead of 1 would provide a much more or much refined result when I bump up the number of refinement layers to like 5. As you can see, it's using 3 offsets, but it's being refined 5 times as it approaches the geometry from the global to a local region. So this is the advantage of Equidistant Mesh. It's basically providing the user with the ability to refine the mesh near the surfaces or volumes of a geometry. And that concludes my list of enhancements for 2016. As you can see, just to quickly summarize, we went through the structural simulation enhancements such as intermittent fixture, the new blended curvature-based mesh, the ability to section the mesh and visualize the results at the same time, bonding between non-touching shell edges, and the best of all is ability to identify unconstrained bodies in a structural simulation. With the plastics tool, the introduction of runner domain, the overall improvement in the interface, enhancement in the reporting tool, the really slick HTML version, and the 6M solver, which basically improves the accuracy, reduces the calculation time for the injection molding simulation problems. Under flow simulation, we saw the ability to visualize symmetric results, the idea of nested iterations, which limits the number of iterations between every time step calculation in a transient solver. The ability to import sunlight properties for solar radiation projects, and last but not the least, the equidistant mesh allowing the users to more efficiently and more accurately model refinement zones or recirculation zones right around the surface or volumes of a geometry. All these enhancements put together is going to help the SolidWorks simulation community solve complex problems faster and easier in 2016. And that perfectly aligns with the other enhancements in terms of design collaboration and building data for manufacturing in SolidWorks 2016. With that, I conclude my presentation. I thank you all for your time, and I believe it's time for questions.
That's right. Thanks, Krishna. That was a great presentation. All right, now's your time to get all your questions answered. We'll wait here for a little bit and see what comes through. Krishna, tell me, with this new SolidWorks 2016, what is your favorite update for the sim?
I think I had put my favorite updates at the end for every single tool. So for my structural simulation, unconstrained bodies is probably my favorite of all, because that saves so much time. The user doesn't have to manually check every single component, whether it's been constrained or not. You can just use the animation tool. For flow simulation, Equidistant Mesh, and for plastics, the new solver, which is going to save the users a lot of time and improve the accuracy of results.
Right, sounds good. Right, are there any questions out there? You're very lucky. You have the Sim Master today.
Typically, when there are no questions, I would assume either the audience are sleeping or I'm way too awesome. And I like to go with the second one all the time.
I agree. You are just way too awesome. You have stunned them all into silence. They just couldn't believe it. You're the Jedi Master of Simulation, Krishna. That's what it is.
Wow. That's an honor. All right. I don't think there are any questions from the audience.
I don't think so either. You have answered them all. Your presentation was so fabulous. Well, I just want to thank you all for joining us this afternoon, and I hope you have a wonderful rest of your day. Bye-bye.